Okay, we have here today a pretty tricky looking integral. We've got the integral from 0 to 1 of 1 over 1 minus x to the 20th dx. Okay, I got the idea for this based on a video from Andripula, except the problem in his video was the indefinite integral. So there was partial fractions involved and it looked pretty messy. I didn't try that. What I want to do was an easier integral instead. I'll provide a link in the description to what he did and let me know if you're able to do it that way. Let me know if you're able to do partial fractions on this or do something for the indefinite integral. So getting started with this, my idea for this was adding these bounds in from 0 to 1 and then thinking I could maybe use the beta function. So here we have our formula for the beta function. This is just kind of one of many formulas for the beta function, but this is the one that's going to be useful to us because we've got the exponent here on the x. And what I can do is, first I want to divide off this n because we don't have anything in front here. So I'm just going to write this as 1 over n over here and get rid of this. What I want to do is take my integral and get it more into this form. So I'm just going to rewrite it. I'm going to bring this into the numerator, so I'm going to write this as 1 minus x to the 20 to the minus 1, so we're matching this part. And then we'll just create this x term. We don't have this, but if I have an x to the 0 here, that's going to work fine. And then all I'm going to need for this, I'm going to need an n value, I'm going to need z2, and I'm going to need z1, but those are all going to be pretty easy to find. So starting with our n's just the exponent here, so our n's just going to be equal to 20. Now we can use this equation equating this to 0. So we're going to have n times z1 minus 1 equals 0. But actually n's 20, so let me just throw that in there. And if you just solve this for z1, we'll find that z1 needs to be 1 over 20 here. And then we'll do basically the same thing for our z2 values. So we're saying z2 minus 1 is going to be this exponent, which is minus 1. And then if I solve this for z2, we find z2, of course, has to be 0. So now we have everything we need here. Okay, what I'm going to do is just take this and let's go back to our formula here for our solution. So it's going to be, for our n, we're going to have 1 over 20 here. This is going to be gamma of z1, so gamma of 1 over 20. Then this piece is going to be gamma of 0, and then we need the sum of these two things. So we're going to have gamma of 1 over 20 plus 0, or gamma of 1 over 20. Now, gamma of 1 over 20 would be really hard to calculate, but I'm glad we don't have to because this is just going to cancel off here. And all we need to find is gamma of 0 over 20. Now, we want to get this in terms of a numeric solution. We've got this gamma of 0 to deal with. What I want to do is we have this formula that we can say gamma of n. We can write this in terms of factorial. So this is going to be the same thing as n minus 1 factorial. So if we're looking at gamma of 0, that's going to be the same thing as minus 1 factorial. But what's minus 1 factorial going to be? I don't really know what to do with that. What we can do is we can go back to our definition of the gamma function, and we can try to see if we can calculate it as an integral. Okay, so here in blue, we have our definition for the gamma function. Now this is usually pretty nice because we just have our input here, this z value, and I can just plug this in and then we just have another integral. If I can solve that, then we can plug it in here, finish it off. Good. So then let's see what happens if we have gamma of 0. So that we're integrating from 0 to infinity. I plug a 0 in there. This becomes x to the minus 1 times e to the minus x dx. If you want, you could write this all in the denominator. I kind of like it better that way, I think. I could write this as dx over e to the x. But this integral right here is actually a problem. Now the thing is, because we're starting at 0, the infinity part of this is actually fine because you plug infinity in here and this thing's going off to 0. But the trouble is when you plug in 0, you're dividing by 0, essentially. And so the graph of this thing, just very roughly, it's something like this. And so the problem we have with this integral is it doesn't converge. So we actually don't have a value for gamma at 0. And not only that, it's a problem at like any negative integer. If I put in like, this thing here is just going to become an integral from 0 to infinity. Just using the formula, this becomes dx over x cubed e to the x. The graph is going to look really similar to this. And again, this doesn't converge. And so it turns out for 0 or any negative integers, the gamma function is not defined. And so we really can't do this here. So this integral here overall does not converge. One last thing I wanted to mention on this that I thought was pretty interesting is if you wanted to look at the graph of the gamma function, you could see it, you go into Wikipedia and see it, but you also, if you put x factorial into Desmos, you won't just get the graph of the integer factorial. You won't just get the, 2 factorial, 3 factorial, 4 factorial. It'll let you graph the gamma function and you'll see it's continuous for all positive values. But then you'll see a bunch of asymptotes at 0 and all the negative integer values. So you'll see where the gamma function's undefined. Okay, so just thought it was an interesting example of where the beta function is not really going to work for us and the gamma function is not going to really work for us. So we'll stop it there. Thanks everyone for watching today. Please like and subscribe. Have a great day.